It turns out that molecular shapes have everything to do with the behavior of molecules, ranging from reasonably simple things like water, which turns out has some very special properties, on up through all kinds of stuff, all the way to more complicated, much more complicated molecules like how DNA functions to carry and transfer genetic information. So what we're going to do is we're going to take our good old electron dot model, the Lewis dot model that we've used in the past, and we're going to expand it a bit, and we're going to use this to predict and help explain the shapes of molecules. And this model, this expansion of the model, depends upon noting that where we have electrons, those are negatively charged, and so one group of electrons and another group of electrons are going to repel each other. Regions of high electron concentration repel each other, and we end up having the most stable or lowest energy molecular structure formed when these electron groups are as far apart as possible, and this is going to minimize the repulsions between them. Once the electron groups have gotten as far apart as possible and minimized their repulsions and achieved the lowest energy state, that is going to let us determine the shape of the molecule. And here we have several molecular shapes. So the gray represents a central atom. The red represents atom it's bonded to, and then the little stick in between is essentially the bond, the electron density that's gluing these things together. So here we have two groups of electron density, two bonds in this case, and they get as far apart as possible by being on opposite sides of the molecule. And I think you can see that this looks clearly like a shape that's a straight line, so we call it linear. Now if we have three electron groups around a central atom, so one's here, one's there, and one's there, total of three, that ends up getting those groups get as far apart as possible by forming a triangle. And this is a flat triangle, so we call it planar triangular or planar trigonal. Both terms are used. If we have four electron groups, so here's an electron group, there's a second electron group, a third, and a fourth, it turns out for those to get as far apart as possible gives us a shape that we call tetrahedral. And hopefully here you can see a little bit of the three-dimensionality of this. We often draw our molecules on a flat plane, on a piece of paper, or on a board, but they're really three-dimensional, and so this is essentially a tetrahedron, four-cornered pyramid, and that's why we call the shape tetrahedral. And there's other shapes we'll see in just a bit. So this is the basis for our new improved theory, which is called the valence shell electron pair repulsion theory, VSEPR for short. Some people call it VSEPR theory. And here are the most common names and shapes shown here. So we have a linear arrangement, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And they have respectively 2, 3, 4, 5, and 6 electron groups around the central atom. And these are shapes and numbers of electron groups that you're going to need to do some practice with and get familiar with, and hopefully pretty soon you'll get the general idea and become expert in this. And the way to help you develop your understanding is to look at some examples. So what is the shape of a CF4 molecule, carbon tetrafluoride? Well, hopefully, and just let's get rid of that for a second, hopefully you can draw the Lewis dot structure. And so you should say carbon's probably going to be the central atom surrounded by 4 fluorines. Carbon has 4 valence electrons, fluorine has 7, but there's 4 fluorines. And if you add that up, you get 4 plus 28, or 32 valence electrons. And then when you draw the Lewis dot structure, it looks something like this. And of course, we could have lines instead of pairs of dots or pairs of electrons in between atoms. Now, once you've drawn the Lewis dot structure, you need to look at how many electron groups there are around the central atom. And so note, we're only picking the electron groups that are around the central atom carbon. We're not worrying about electron groups that are farther outside on these fluorines, for example, because these are not attached to anything, but the fluorine is attached to the carbon. And so here we have 4 electron groups, or 4 charged clouds. And when we have 4 charged clouds and all of them bond to something, then it looks something like that. And that's one of the shapes we've seen before. One charged cloud bonded to an atom, a second charged cloud bonded to an atom, a third, and a fourth. And that is the shape that we call tetrahedral. Now, we can also determine whether this molecule is polar or nonpolar. And we've already talked about bonds being polar and nonpolar, and please note now we're talking about molecules being polar or nonpolar. So carbon and fluorine make a bond that is polar, and we can represent that by a little arrow to represent the dipole. So since fluorine is more electronegative than carbon, if you look up on the electronegativity table, it's 4.0, carbon's 2.5. So there's a dipole pointing from carbon to this fluorine atom. This side is a little more negatively charged. The carbon's a little more positively charged. But note, there's a dipole pointing to this fluorine, to that fluorine, and to that fluorine. And if you are able to ever play with a physical tetrahedral molecule, or if you look at the pictures that look a little more three-dimensional, you'll see that this is really symmetric. And so this pull, that pull, that pull, and that pull of electrons towards the fluorines, they essentially all cancel each other out, and the overall net dipole, which we could represent by an arrow for the whole molecule, turns out that there isn't any. All of these cancel out, and the overall net dipole is 0, and we therefore say that the molecule is nonpolar. And please note, here we're doing a molecule and its polarity, not the bonds individually. So we use the bond polarity to get to the overall molecule polarity, and those are somewhat separate questions. Okay, let's do one more example. What's the shape of a CS2 molecule? Well, we draw the Lewis dot structure first. You might want to pause the screencast and see if you can draw it correctly. And then hopefully you drew something like this: 4 valence electrons for carbon, 6 for each sulfur. Ends up having to have double bonds in between carbon and each sulfur. And another way to draw it is with lines for the double bonds. And now, if we determine the shape of the molecule, we want to first of all find out how many electron groups there are. And in this case, there are 2 electron groups. And note that a double bond counts as 1 electron group. So this is a group of electrons, there's a second group of electrons, and we only worry about electrons that are around the central atom. And if you go back to this way of drawing it with the dots, that 4 electron grouping is 1 group of electrons. And this 4 electron grouping is a second group of electrons. We only have 2 total electron groups, and the shape that has 2 electron groups around the central atom, perhaps you remember, and maybe if you look at the model here, you can sort of visualize that that's going to be called linear. And let's do one other thing with this molecule, which is to ask if it's polar or nonpolar. And in this case, it turns out when you look up the electronegativities of carbon and sulfur, they're basically the same. So there's no dipole between carbon and either sulfur. So the molecule, this one, would have to be nonpolar. But let's just suppose, hypothetically, that instead of sulfur, maybe this was an oxygen atom on each side. So instead of CS2, maybe this would be CO2. So replace the sulfur by an oxygen. And if that was the case, then oxygen would be more electronegative than carbon. There would be a dipole from the carbon towards that oxygen. But there'd also be a dipole towards the other oxygen, and they'd be equal and in opposite directions, and they would therefore cancel out and give us an overall nonpolar molecule. So far we've seen two examples of molecules where the individual dipoles cancel out, or would have in the second one if they had dipoles. We will see in future screencasts that that doesn't always happen. Sometimes the dipoles don't cancel out and we get a polar molecule, so stay tuned for that.